You know that moment when you're walking down the street, maybe on your way to grab a coffee, and you see it? A crack. A big, jagged crack, snaking across the sidewalk. Or maybe it's that patch of road that's been perpetually under construction for months, looking more like a minefield than a commute. We've all been there, right? It's just normal. Potholes, crumbling buildings, the constant need for repair. It's like a background hum to modern life. You expect it. You budget for it. You sigh about it. But have you ever really stopped to think about why? Why is the very foundation of our modern world, the concrete holding our cities together, so temporary? Because here's the mind-bending part. For centuries, the Romans were building with a material that just didn't do that. Their concrete. It's still standing. We're talking aqueducts, the Pantheon, entire harbors, structures that have endured earthquakes, tsunamis, and nearly 2,000 years of history, looking practically new in some places. It's almost as if they stumbled upon some ancient secret, a recipe for forever concrete. And we've been scratching our heads trying to figure out how they did it. Why did their concrete last for millennia, while ours often struggles to make it 50 years? What was in that Roman mixture? And more importantly, can we bring it back? Today, we're going to pull back the curtain on the baffling durability of ancient Roman concrete, and what we find might genuinely change how you think about the very ground beneath your feet. Seriously, stick around. It's way weirder than you think. Okay, so let's talk ingredients. What was this magic potion the Romans were brewing? For a long time, scientists thought it was just their specific ratio of lime, volcanic ash, and water. And sure, that's part of it. But the real aha moment came from a study published in the Journal of Archaeological Science back in 2020. Researchers at the University of California, Berkeley, decided to really dig into the composition of this ancient concrete, looking at samples from places like Privernum, an ancient Roman town. And what they found was unexpected. They noticed that the ancient Romans weren't just mixing volcanic ash in. They were using a specific type of volcanic ash called pozzolan, which is rich in silica and alumina. But here's where it gets interesting. When they looked closely at the hardened Roman concrete, they didn't just see a uniform paste. They saw these little white chunks. And when they analyzed these chunks, they discovered they were actually quicklime, a component that's supposed to react vigorously with water. But in this concrete, it had apparently just sat there, dormant, waiting. Now, you'd think this would make the concrete weaker, right? Like finding a solid piece of flour in your cake mix. But the UC Berkeley team, led by researchers like Dr. Brenda Culver, found that these lime chunks were the key. They hypothesized that when tiny cracks formed in the concrete over time, cracks that are inevitable in any material subjected to stress, water would seep in. And that's when the dormant lime chunks would finally react. They would dissolve, creating a calcium carbonate solution, which would then recrystallize. And get this recrystallization process would actually fill the cracks. We're talking about a material that literally heals itself. It's not just strong, it's alive in a way. Can you imagine if our roads could do that? Fix themselves? We'll get to why that's so revolutionary in a bit, but first, let's consider how this contrasts with what we do today. So, we have this ancient concrete that heals itself. Now, let's contrast that with modern concrete. We've gotten pretty good at making concrete strong, sure. We use Portland cement, which is a highly refined product. But the way we make it and the way it behaves is fundamentally different. Modern concrete is typically made by mixing Portland cement, aggregate, like gravel and sand, and water. The cement hydrates. It chemically reacts with water to form a paste that binds everything together. This process is fast, it's efficient, and it creates a very strong, very rigid material. But that rigidity, that lack of flexibility, is also its downfall. When stress is applied, or when temperatures fluctuate, modern concrete expands and contracts. And because it's so rigid, it cracks. Then water gets in, freezes, and expands, making the cracks bigger. Salts can seep in and chemically attack the concrete. Essentially, once a crack forms, it's a one-way ticket to deterioration. Think about that 33% figure the FAO throws around. That's the percentage of global arable land that's been degraded. Much of that degradation is linked to unsustainable practices, and while concrete isn't soil, the principle of a material failing under stress and environmental impact is similar. We have to constantly repair, replace, and rebuild. It's a massive economic drain and an environmental burden. We're essentially building with a material that we know will degrade. The Romans, on the other hand, weren't just building structures. They were building with a material that was designed to endure. They achieved this not by making it more rigid, but by incorporating a mechanism for resilience. It's like comparing a perfectly brittle glass sculpture to a piece of bamboo that bends but doesn't break. And the ingredients they used? Volcanic ash was readily available in the Italian landscape. They weren't importing exotic, highly processed materials. They were using what was around them, and they understood its properties so intuitively. It makes you wonder, what other ancient secrets have we overlooked in our rush for industrial progress? I mean, think about ancient farming techniques. The FAO reported in 2019 that traditional practices like crop rotation and composting are vital for soil health. Practices we're only now rediscovering because we've degraded so much land. The Romans seem to have had a handle on sustainability long before it was a buzzword. So, why did our concrete take such a different, less durable path? Okay, let's circle back to those lime chunks, or lime clasts, in the Roman concrete. This is where the science gets truly fascinating. Remember how I said they were dormant? Well, when the Romans made their concrete, they likely used a process called hot mixing. They would heat the lime to a very high temperature, creating quicklime. Then, they would mix this quicklime with volcanic ash and water. The reaction between the hot quicklime and the volcanic ash created a stable binder. But the key was that the lime wasn't fully slaked, meaning it hadn't fully reacted with water during mixing. It remained in this highly reactive, partially unhydrated state. Think of it like a coiled spring, ready to unleash its energy. Now, imagine a tiny crack forms in this Roman concrete. Water, the enemy of modern concrete, becomes the hero here. When water seeps into the crack, it finds those lime clasts. This is where the magic happens. The water reacts with the lime, dissolving it and forming calcium hydroxide. This liquid then interacts with carbon dioxide from the air and water, precipitating calcium carbonate. This calcium carbonate then recrystallizes, forming new mineral crystals, often calcite. These new crystals grow, effectively bridging the crack and sealing it. It's a self-healing process. It's like the concrete has an internal immune system, but it's even more sophisticated than that. The UC Berkeley study also found evidence of calcium-rich fluid that flowed into these fractures, incorporating surrounding volcanic ash to create a calcite precipitate. This fluid seems to have been generated when the lime clasts reacted with water. So, not only was the lime healing the crack, but it was also using the surrounding volcanic ash to reinforce the repair. It's this continuous, low-level reaction that keeps the concrete strong and resilient over centuries. It's not just a static material. It's a dynamic system that responds to its environment. Unlike our modern concrete, which just passively waits to break, Roman concrete actively repairs itself. It's a level of material science we're only beginning to replicate. The implications of this for modern construction are enormous, but we have to understand why we moved away from this approach in the first place. Okay, so we have this incredible, self-healing concrete. Why aren't we using it? This is where it gets genuinely weird and, honestly, a little depressing. For decades, scientists have known about the Roman concrete's superior properties. They've analyzed it, written papers, like that one in the Journal of Archaeological Science in 2020. They've even tried to replicate it. But replicating it perfectly, at scale, for modern construction demands? That's the challenge. The precise sourcing of volcanic ash, the specific, hot mixing technique that's more labor-intensive than our current methods. It's complicated. But here's the part that nobody talks about enough. The shift to modern Portland cement wasn't just about creating a stronger material. It was about efficiency and speed. The Industrial Revolution demanded it. We needed to build faster, isn't just about old buildings. It's about building a future that lasts. So, what can we actually do with this information? It's not like we can just pull a switch and rebuild every city with Roman concrete tomorrow. But there are concrete steps we can take. First, we need to invest more in researching and replicating these ancient self-healing properties. Scientists are already working on self-healing concrete, using bacteria or microcapsules, inspired by these ancient methods. We need to push that research forward and explore how to scale it affordably. The UC Berkeley study and others like it are crucial starting points. Second, we need to reevaluate our construction standards. Maybe faster and cheaper shouldn't always be the primary drivers. Durability and sustainability should be weighted much more heavily. This means incentivizing the use of materials and techniques that have a longer lifespan, even if the initial cost is slightly higher. Think about the long-term cost savings of a structure that lasts centuries versus one that needs major repairs every few decades. And third, we can advocate for smarter infrastructure. When you see those potholes, those crumbling sidewalks, it's not just an inconvenience. It's a symptom of a deeper problem. Supporting policies that prioritize resilient infrastructure and sustainable materials is key. It's about demanding that our built environment is as enduring as the lessons from our past. We're learning from ancient water purification methods, which can remove up to 90% of contaminants, to solve modern water crises, who reports 844 million lack clean water. We're looking at ancient navigation, like celestial navigation, to improve modern systems. This concrete is just another piece of the puzzle. Ancient ingenuity is still incredibly relevant. So next time you see a crack in the pavement, don't just sigh. Remember the Romans. Remember how they built with materials that actively fought against decay. It turns out, some of the smartest technology isn't new, it's just forgotten. And perhaps, by rediscovering these ancient secrets, we can start building a future that, unlike our current concrete, might actually last. What other ancient technologies do you think we've lost that could solve modern problems? Let us know in the comments below. And if you found this journey into the past as mind-bending as we did, make sure to subscribe to Not a Simple Question for more deep dives into the seemingly simple. We'll see you in the next one.